Hi, and welcome to our Cloud Next session on load balancers. And today we're going to be talking about the next generation of our cloud load balancers. We've introduced many new features recently, and we're excited today to share with you some of what those features entail. But first, let me present to you our presenters. So Adam Michelson, I'm a product manager at Google Cloud, and I help run the cloud load balancers. Babi, do you want to introduce yourself?
Hi, everyone. I'm Bobby. I'm also a product manager on the load balancing team. Thank you, Adam.
Awesome. So with no further ado, let's dive right in. So today we're going to talk to you about three items. One is next generation load balancing. We've been working to re-platform many of our load balancers to include advanced traffic control capabilities. Our load balancers have been re-platformed to run on top of the Envoy open source system. And if you're familiar with the Envoy system, then many of these features may be familiar to you. And if you're not, that's totally fine. You don't need to know that platform to use our cloud load balancers. We'll also be talking about how using this common platform will enable you to have common capabilities across our load balancers, as well as common control planes across our load balancers. Next, we'll also be talking about load balancing everywhere. This is a feature where if you have services that run off of Google Cloud, such as on-prem or in a multi-cloud environment, how you can connect to those services through our load balancers. So if you run services that are not running on Google, you can still access those services via our load balancers. And finally, we're going to talk to you about some of our enterprise-ready features, such as Private Service Connect, which enables you to connect to third-party or services that are not necessarily under your organization's control, as well as how you can connect to third-party applications. So first, we're going to talk about some of our next generation load balancing capabilities. So for the folks who may not be familiar with our load balancers, this is a quick overview of our load balancers. We have a few load balancers in our load balancer fleet. We have both a set of level 7 HDPS load balancers, as well as level 4 network load balancers. Most of the next generation capabilities you're going to see in our level 7 load balancers. So as we were saying, many of our load balancers are getting an upgrade where we have advanced traffic control capabilities brought by Envoy. Now, Envoy, as I said earlier, is an open source platform. If you're familiar with the Envoy platform, then again, these services may be familiar to you. One of the commitments Google has is to the open source community. And this is an example of that, where we work with the Envoy community to contribute features back to that community, and then we consume those features into these load balancers. So as part of that capability, you'll see our load balancer have consistent set of features, also consistent with the open source capabilities. And through that consistency, you'll see common control planes, common observability, and common feature set throughout our load balancers. In the initial release of our load balancers that support Envoy, you'll see many new features. Here on the right, you'll see examples of what those are. I'm not going to go through all of them, but I'll call out a couple. So one example is weighted traffic splitting. Weighted traffic splitting is used when you roll out, for example, a new feature or a new service, and you want to test that service, such as running a canary test across those services. Weighted traffic splitting allows you to take a certain percentage of your traffic, 1, 2, 5, 50%, what have you, and push it to the new service you're rolling out. Another example is fault injection. In this example, you can emulate what would happen if you had a fault in your system before it happens in production. That way you can harden your deployment to make sure that when errors do inevitably occur in production, you've had an opportunity to test them using fault injection as an example. Now, this advanced traffic control capability of our load balancer actually extends beyond just load balancer capabilities. For those who, again, may be familiar with using something like an Envoy sidecar, this example may be familiar to you. For those who are not, Envoy, again, is an open source component and platform which handles traffic management. We have some of those capabilities built natively into our load balancers. And again, you don't have to understand Envoy at all to use our load balancers. They're just native features of our load balancers. But for deployments that are heterogeneous by nature, multi-cloud, or on premises, and you want a common feature set of traffic control across cloud and on premises or multi-cloud, and you want common policy management and control, you can deploy what's called an Envoy sidecar, which is a deployable piece of code that can deploy next to your services, and those sidecar will contain traffic control capabilities. And if you wish, you can use a component such as Google's Traffic Director, which is a managed control plane that can push XDS configurations and controls into your sidecars. And it doesn't have to be Envoy, it just has to be an XDS compatible service. So if you do that, then you can have some services sit behind Google Cloud load balancers and other services that have a sidecar sitting next to them in Google Cloud or on premises or on multi-cloud. And in that sort of architecture, you can handle a highly distributed set of systems running across heterogeneous systems, but running as if they're running in a homogeneous environment because they're all standardized using the Envoy traffic control capabilities. They'll have common features, they'll have common control planes, they'll have common observability. Let's run through a quick example of how this might be useful. So in this case, imagine you're an e-commerce provider and you have a shared service across many components, in this case, a wallet service that could be maybe a payment processing engine. Now here we have an e-commerce engine that will use the external global load balancer to access that service. We also have potentially a call center using an internal load balancer, which is again hitting the same common service. And on the right side of this picture, you'll see potentially this point of sale using regional load balancers. Or maybe there's nightly batch jobs running on premises, maybe running fraud protection. So in all these cases, you have a common service that these various systems are using. So what happens if you want to roll out a new service, a version 2 of the wallet? Each of these disparate systems need to be able to test that service using something like a canary test. That's pretty complicated to do if each of these systems has its own capabilities, and some may or may not have weighted traffic splitting, for example, built in. But if you're using something like an Envoy platform everywhere, then you can use a common weighted traffic system across all these systems. This will be the same capability, the same control planes, the same observability to see if features are working or if they're not working. And in this way, you can go ahead and test a secondary wallet service, say version 2, and see if that service is working as expected. And once it is, then you can push all traffic to that new service. And so in this way, if you do have a highly distributed set or a complicated architecture that has reusable services, whether it be just a distributed set of services or a system like Service Mesh, you can use advanced traffic management that's built natively into our load balancers and other components to reduce the toil and overhead of managing a highly distributed set of services. So now what I want to do is run you through a quick demo to see this live in action. In this demonstration, we're going to see how to roll out a canary test. Here we see 4 different services. In the upper left, a global load balancer, lower left, regional load balancer, upper right, an internal load balancer, and in the lower right, we see a sidecar proxy. Here we're rolling out the various commands required to be able to do our canary test. Now we're seeing that some traffic is switching over from version 1 to version 2. Over the course of about 30 seconds or so, all the various traffic management solutions, load balancer and sidecar proxies, are beginning to send their traffic to both version 1 and version 2. The purpose is to make sure that version 2 is handling traffic properly. At this point, we see a lot of traffic going to version 2, so now we're going to say that everything is working properly, and we're going to send all of our traffic now to the version 2 and away from version 1 and do our full rollout. So again, we have the same 4 services, and we're going to run the commands, which are going to be common across these various services, to be able to switch our traffic onto the new updated version 2 wallet service. And once again, it takes about 30 seconds or so for all the services to get their command and to switch all their traffic over to version 2. And so now you see that all the traffic at this point has been switched to version 2, and our Canary rollout is complete. Now that you've seen how the next generation of load balancers can enable advanced traffic management capabilities across a highly distributed set of services, I want to turn the conversation over to Babi, who's going to run you through some of our capabilities around load balancing everywhere. Babi?
So one of the goals of our cloud load balancing is to meet you where you're at in your journey to cloud. And as part of that, we have gone ahead and introduced hybrid load balancing. So what is hybrid load balancing? You have clients that could be external to Google or internal. They send traffic to our external HTTPS load balancing or external TCP proxy, or our internal HTTPS load balancing. These load balancers have backends, of course, on Google Cloud, but now we've enhanced them to also support backends on-prem and in other clouds. These on-prem and other cloud backends are connected to Google, either via public connectivity across the internet or via private connectivity through HAVPN or interconnects. What we're really excited to share with you is that we have now in public preview our hybrid load balancing with support for on-prem and other cloud backends via private connectivity, and we support health checking of these backends. And we'd really like for you to try them out. So how are some of our customers using hybrid load balancing? What are some of their use cases? The most straightforward use case is load balancing to workloads on-prem. More concretely, you can imagine an ERP application running on-prem in a regional extension connected to Google via partner interconnects. The second use case is protecting your on-prem workloads against DDoS attacks with Cloud Armor. Or you can use identity-aware proxy to authorize access to your on-prem resources. You can enhance the latency experience for your end users by caching static content on CDN. The third use case uses weighted traffic splitting that Adam had alluded to earlier to do a gradual migration of workloads from on-prem to Google. Now, we are working on additional use cases, such as supporting failover from on-prem to Google. As we develop more and more, we shall share them with you. Now, let us turn our attention to how we are enhancing our enterprise users with hybrid load balancing use cases. So what we are focused on is reducing the operational toil and meeting the scale and security requirements for our enterprise users. In this regard, first, let us look at Private Service Connect. So what is Private Service Connect? You know, in typical customer deployments, you have multiple teams producing services for consumption by other teams. The groups offering these services could be part of the same organization, or they could be third-party services, or services offered by Google. The way you typically set this up securely is via private connectivity by setting up peering between the producer and the consumer. But you run into a lot of operational toil and scale constraints with peering. Now, this is where Private Service Connect comes in. It is our converged service connectivity offering. Because it does this through private connectivity, it is secure. You don't have the scale constraints that you have with peering, and it can scale to thousands of endpoints. It is also very performant. You get line rate because there is no proxy in the middle. Now, how does this Private Service Connect actually work? Well, you have a producer and a consumer. In the producer, you set up the service behind a load balancer and a service attachment point in the producer's address space. This service attachment point is linked to endpoints in the consumer's address space. The workloads in the consumer wishing to access the endpoints simply send traffic to the endpoints in their own address space. So how does load balancing work with Private Service Connect? Let's start with the producer. The internal HTTPS load balancer and the internal layer 4 load balancer helps you scale out your service and makes it highly available. Now remember how I was referring to hybrid load balancing? The internal HTTPS load balancer now supports endpoints on-prem. So you can use the Private Service Connect to offer a service residing on-prem securely without having to worry about overlapping IP address space. On the consumer front, we are now working on putting these PSC endpoints behind our HTTP load balancers, external or internal. With the URL maps that are associated with this HTTP load balancers, you get fine-grained control and selection of which producer services that you route to. You also can now log every service invocation with our HTTPS load balancing logging. In addition, for external services that access the HTTPS load balancer, you can put a cloud armor and protect against DDoS attacks, or use our managed TLS offering to secure the service further. Now I'm excited to share with you another capability that we have enhanced for our enterprise users, and that is integration with third-party appliances. So a lot of our enterprise users, as they migrate to Google Cloud, wish to bring their favorite third-party appliances with them as part of their lift and shift. With our ILB as next hop, we have made it very seamless and scalable integration of these appliances via bump in the wire mechanisms. What we've done is gone ahead and enhanced that with 3 additional enhancements. The first one is support for symmetric hashing. You know, when you have these multiple stateful firewall appliances and you have bidirectional traffic, you need to ensure that the return traffic hits the same instance on the way back. You typically do this by configuring source NAT, but there's a lot of operational toil associated with it. But now, by using symmetric hashing with our layer 4 internal load balancer for bidirectional flows, you no longer have that constraint and toil. The second enhancement that we've done is we've enabled all protocols to flow through ILB as next hop, not just TCP and UDP. So now, by allowing ICMP packets through, we'll be able to support ping and trace routes so that you can better troubleshoot your flows. Last but not the least, we've also added tagging support for your load balancers. What this effectively does is it allows you to group a certain set of endpoints with a tag and associate them with an ILB, and route your traffic from those clients specifically to that ILB. The most common use case has been regionalization, where you can tag all workloads in a specific region and associate them with that ILB in that specific region. We have a very compelling roadmap of our load balancing offerings and features. Let me share some of them with you. If you look at this roadmap across the board, we have multiple flavors and features of our load balancing. What I'd like to bring your attention to is in the security column. You'll see that we've made TLS 1.3 the default for our HTTPS load balancers. With perfect forward secrecy, getting rid of old, less secure ciphers, we made our solution more secure. By cutting down on the handshakes and the setup latency, we've resulted in a much more optimal end user experience. On the scaling front, if you'll notice, we've added support for layer 4 ILB subsetting. What this allows you to do is to scale your backends more than 255 of your layer 4 load balancer, and hence scale out your service much more. Now let me hand it off to Adam to wrap this session up.
Thank you. Thanks so much, Bobby. So I wanted to thank all of you first who joined us today, and I hope you enjoyed our session and found it informative. And I also wanted to present to you other networking sessions that are happening if you're interested in other topics. And of course, with our load balancers, we'd love it if you would have the opportunity to try them out. And we always are interested in to hear your feedback in terms of which features are working for you and what enhancements you would like to see. So with that, I'd like to thank you on my behalf and on Bobby's as well. And we do hope that you enjoy the rest of your next sessions.